Okay, everyone. So the last part of chapter 6 that we're going to be looking at is combining the idea of collision theory with reaction rates. So just to kind of recap what we know already about collision theory, right? So we know that essentially particles are always in random motion, right? So they're always moving and they're at different speeds, of course. Now we know that the average kinetic energy is essentially relative to the temperature of those particles, but each individual particle has their own speed at which they're moving at. So when we have a chemical reaction, there's really two things that need to happen. You need to have collisions, so the particles have to actually collide. And not only that, there has to be a sufficient amount of energy at the correct alignment in order for that collision to be successful or effective. So an effective collision is another way of saying a successful collision. So you can have collisions happening all the time. Things collide. Of course, think of like air particles, right? So there's oxygen in the air, there's carbon dioxide, there's water vapor, right? Those particles are always colliding with one another, but we don't have chemical reactions happening in the air out of nowhere, right? So what has to happen, not only is the collision have to happen, but the particles have to have a certain amount of energy and a certain alignment or position so that when the particles actually do collide, that the bonds can actually break and new bonds can be formed. Okay, so every reaction has a certain energy threshold that has to be met, right? And we saw that even looking at enthalpy change, right? So we saw a lot of our potential energy diagrams. Here's our reaction process where we had, let's say something like this. So we have our reactants and we have our products. So the amount of energy that has to be put into a reaction, right? So this is what is absorbed by the reactants in order for those bonds to break. And then there's a certain amount of energy that is released. So the difference, of course, we know the difference between those two portions is our delta H, right? So the energy in versus the energy output. Or you can think of like the H of the enthalpy of our products minus the enthalpy of our reactants, right? It gives us our overall delta H. So what we're looking at here, though, the focus is when we're talking about the energy required, we're looking at that energy input. This is the energy requirement for a successful collision. So let's say, I'm going to make up a number, 20 joules have to be absorbed by the reactants when they actually collide. That means when you have that collision, if you don't have at least the minimum amount of 20 joules, the collision will not be successful. You're not going to have your products that are formed. So it's important that when we're talking about collisions, we make mention of the fact, of course, we mean successful collisions. And not only that, but we also have to put into consideration the angle at which the collision is happening. So you might have enough energy, but you may not have the correct positioning for that reaction to occur. So this is just a little diagram to kind of prove that point. So here we have nitrogen monoxide, nitrogen trioxide combining to make nitrogen dioxide. So here are our reactants. So here we have no reaction, right? And the molecules are twisting and turning in each different way. So here we have, this molecule is twisted a little bit, still no reaction, no reaction, no reaction, until finally we have the correct positioning that with the correct amount of energy where we can have an effective, successful collision. So it's kind of all these things that have to come together for a product to be formed. We don't really think about that usually. Usually, we just put some reactants together and it happens. But, of course, not everything that you simply put together will necessarily react. So I've already mentioned this to you about the example with air, right? So there's things that are colliding all the time, right? Nitrogen and oxygen in the air, like the air is an 80% nitrogen. It's colliding all of the time to interact with oxygen and other things in the air, but we don't have reactions occurring, right? If that were to collide and make nitrogen dioxide, that's a toxic gas. So it's not like you're walking down the street and you're worried they're going to go into a cloud of toxic gas. It's because simply those reactions, those collisions that are happening, they're ineffective. They are not successful collisions. Okay, so here's some terminology. I may have mentioned this when we did the beginning part here, where we looked at reactions and rates of reactions. But anyways, that threshold of energy that I was talking about, that minimum amount of energy required, has a certain specific term. It's called activation energy. So the activation energy for a reaction is the minimum energy requirement in order to have an effective collision. So when you're looking at a diagram like this, your activation energy is actually this energy requirement right here. So it would be essentially, what is the energy threshold for that reactant to kind of get over the energy hump, potential energy hump to get to the product side. So here's another example, right? So here's a potential energy diagram. Right here are our reactants. Here we have our products, right? So we have our activation energy required, and then of course we know the difference between those two is the delta H, right? The difference between energy input versus energy output. So at the top of the activation energy, or in between that moment of time between reactants and products, this is known as the activated complex. And actually we saw this already in chapter 5. Essentially, this is the moment in time when the bonds have now been broken from our reactants, but the products have not yet formed its new bonds. So essentially, it's not really anything. It's not a reactant. It's not a product. It's kind of like a jumble of atoms. It's in the process. This is the process, basically, of the in-between moments of time where bonds are broken, but new bonds are not yet formed. So when you're talking about this activated complex, it doesn't really have a term. There's no name for it. It's really just a jumble of atoms. It's kind of like the broken bonds are here, but the new bonds are not there yet. So you may have reactions that occur in more than one step. So you may have more than one activated complex that is happening. But of course, it depends on the reaction mechanism that we're talking about. So catalysts, we looked at this in section 6.2. A catalyst is really something that is added to a reaction that really will lower the activation energy. So let's say here I have two different things happening, right? So the red might be the activation energy, and the symbol for activation energy is capital E with a subscript A. So this would be with no catalyst, right? And then, of course, when we add a catalyst, what happens is the activation energy is now lowered. So all that really means is that the percent of successful collision. Okay, sorry about that. Okay, so what that means is really the percent of successful collisions goes up. So the number of collisions does not increase, right? We're not actually changing how many collisions are actually happening, but what we're simply doing here is the percent of success has gone up because the threshold has now lowered. So maybe before it was 25 joules and now it only needs 15 joules. So that means before, when we had a collision, let's say a collision happened with 20 joules worth of energy. So previously, with no catalyst, 20 joules worth of energy would not cause a successful collision. But now with the catalyst, 20 joules worth of energy is enough for it to actually be successful and make products. So that's kind of how a catalyst would work here. Okay, so reaction mechanisms is actually a term we have seen. Maybe I didn't call it a reaction mechanism yet, but you've seen this type of thing already when we did our Hess's Law problems in chapter 5. So reaction mechanism is really, it shows essentially the pathway of reactions that will lead to our overall reaction itself. So reactions very rarely happen in one step, okay? Especially if you have more than 3 things that have to come together. So for example, if I had just simply A plus B making C, this can happen in one step, no problem. I have 2 things that have to collide. However, let's take a look at this reaction. So for this reaction to happen, we need 4 HBr and 1 oxygen. That means in total, 5 different particles have to come together. Okay, so not only do they have to come together, they have to collide at the same time with the correct angle, and we have to have a sufficient amount of energy. So this is very rare to happen. Like this, basically, if we were relying on these 5 things to come together with the correct energy at the correct angle, it may never happen. Okay, but luckily reactions don't really happen in one step when they are involving this many things. So, for example, this exact reaction actually happens in 3 different steps. So this is what I mean by a reaction mechanism. And you've seen this in Hess's law. In Hess's law, we look at reaction mechanisms and we try to achieve the overall reaction. So actually, this exact same mechanism here will give us this. So if we were to cancel out things that we can, right? Just imagine this is like a Hess's law, right? Our Huber and our Haber would go. And then we were left with, there's nothing else. So we have 1, so this is by 2. So this is 1, 2, 3, 4 HBr plus our O2 makes H2O. And there's 2 of them. This whole line is multiplied by 2 and 2 Br2. Right? So essentially this is a mechanism. So what does this mean? So the mechanism actually can tell us a bunch of information. So first of all, each step in this mechanism has its own requirements. So remember we mentioned a certain angle, a certain amount of energy, and they have to collide. Well, the amount of energy required for step number 1 is not necessarily the same amount of energy requirement for step number 2. So you're going to have different energy thresholds for each one. Each one has its own energy requirement. Now, the reaction that needs the most energy, the highest amount of energy, is our activation energy. Okay, so that's the one. Activation energy is essentially the highest amount of energy required for that entire mechanism. So the ones we looked at over here, this is like a 1-step reaction, right? So we might have, oh, I forgot I had this nice little picture down here. We've seen this picture before. Oh, look at me. I'm just drawing it myself up there when I have this nice thing here. Anyway, so you have here, right, reactants to products. We've seen this before when we looked at factors that affect reactions. Anyway, okay, so let's say we have a 3-step reaction. Okay, so reaction process. So I might have something that looks like this. Maybe here's step number 1, here's step number 2, and then here's step number 3. Reactants and products. So how I can tell right away this is a 3-step problem or 3-step mechanism, each threshold or each kind of like hump is its own reaction energy requirement, right? So from here to here would be the threshold for reaction step number 1. And of course, we know that it goes 1, 2, 3 because this goes from the start of our reaction process to the end of our final product. The requirement for our second step would be from here to here. And the requirement for our third step would be from here to here. So even though there's 3 steps in this mechanism, they each have their own energy requirement. This step right here, the second step, would be our activation energy because it is the highest amount of energy required for the entire mechanism. Okay, so that being said, when you have reactions like this happening that have more than 1 step, the reaction typically is not successful unless the activation energy is achieved, of course, because you're not going to be able to form your final products. Okay, so we'll talk about rates in a second. We'll look in the next part.